Hello and welcome to our 9 a.m. press conference, first results from Axial Seamount, an active underwater volcano. I want to mention that there are 2 associated papers publishing today in Science and 1 paper in Geophysical Research Letters. Our speakers today are Richard Murray from the National Science Foundation, David Clegg from the Monterey Bay Aquarium Research Institute, Scott Nooner from the University of North Carolina, Wilmington, and William Wilcock from the University of Washington.
Thank you. Good morning, everyone, and thanks for coming today. My name is Rick Murray, and I'm the director of the Division of Ocean Sciences at the National Science Foundation. The NSF is the leading U.S. federal agency that funds basic scientific research, education, and technological innovation. So this is a terrific day and promises to be a wonderful event here right now. In a moment, we're going to hear from 3 internationally renowned marine scientists about a series of volcanic eruptions at an underwater volcano called Axial Seamount, located off the Oregon-Washington coast. These folks are going to describe the exciting observations they've made and are continuing to make using a vast array of scientific instruments that are in residence at the summit of Axial Seamount. The instruments are part of a new observing system funded by NSF called the Ocean Observatories Initiative, or for short, OOI. So today we're essentially going to go on a descent to Axial Volcano, where OOI has allowed us to watch the volcano as it builds to an eruption and to view that eruption as it takes place. Before our journey, I'm going to provide some brief background about the OOI network overall. NSF has recently completed building the OOI, which is a networked observatory of science-driven sensor systems to measure the physical, chemical, geological, and biological variables of the ocean, the sea floor, and the ocean-atmosphere interface. The OOI consists of 7 arrays located across the North and South Atlantic and Pacific Oceans, including 1 cabled, 2 coastal, and 4 global arrays. Today, the information about Axial Seamount is going to be information that was gathered by the cabled array. Overall, OOI infrastructure is made up of approximately 80 different platforms carrying over 800 instruments and providing over 100,000 data products. The OOI puts ocean observing data into the hands of a vast user community. Onshore, at sea, vast user community of oceanographers, scientists and researchers, educators, and the public. Access is free, it's accessible through the web, and it's accessible by anybody living on our planet. None of this research would be possible without our university and agency partners, including NOAA, National Oceanic Atmospheric Administration, which initially observed activity at Axial Seamount several years ago. So as these 3 scientists will describe, OOI is providing an unprecedented opportunity for us to understand our planet, the only planet we know of that's habitable for humans. In the process, OOI is taking us to locations like Axial Volcano, places in the sea's depths that might have even astounded Jules Verne, who wrote over 100 years ago, 20,000 Leagues Under the Sea. And now we're able to see it ourselves in the modern and in the future as it's happening. So I will turn this over now to Dr. David Clegg from the Monterey Bay Aquarium Research Institute.
Thank you, Rick. So I'm going to describe a little bit about the eruption itself, but I wanted to get you started with some basic info about Axial Seamount. It's located about 300 miles off the Oregon-Washington coastline. It's shown on the map here. It's very tiny. That's the Oregon coast. There's the seamount out offshore. The volcano is about a half a mile tall and about a mile below the surface of the ocean. It has a summit caldera, which you see here. The color scheme is deep as blue and shallow as orange. That's going to be the same in a couple slides later in the talk. And the eruption started in the summit here, and the green flows are the new eruption in 2015, shown for comparison to the eruption from 2011. This is a very active volcano. It's erupted 3 times in the last 20 years. What else do I? The cabled observatory is also shown on here. Most of the information I'm going to talk about is actually not from the cabled observatory. The instruments on the cabled observatory notified us that something had happened, and so we could respond to it a few months later when oceanographic cruises were scheduled to go out there. So what did we really learn out there? This is a great laboratory to study volcanic processes. It has something that is truly unique in the world. It has a really well-imaged magma chamber. We know where the magma chamber is, how big it is, how much of it is liquid magma, how much of it is crystal-rich magma, and the shape of it. And we can then tie that to the processes that we see happening on the seafloor. On land, that kind of imaging of the magma system is almost impossible to do. So you know what happened, but you don't know the plumbing. Here we have the opportunity to tie the plumbing to what actually happens on the surface. Second, it will have, I think, applications in the long run once we understand how these two systems link to studying hazardous volcanoes on land. Axial itself does not pose particular hazards to us. The eruptions in 1998, 2011, 2015 have increased in volume, frequency, and the temperature of the lava. So the volcano is evolving with time. And it continues to evolve now. It still has a very high resupply of magma, and Scott will be talking about that in a few minutes. The chemistry of the lavas actually mimics the variations that are mapped in the magma chamber underneath the volcano, which again is the first time I know of where that has actually been documented. It has several new styles of eruptions that we didn't really know about that are mildly explosive and might, on volcanoes located in closer to habitated islands, for example, posing hazards that we didn't really understand. So I'm going to show you here, this is, again, the same map, shallow. There's summit eruption, then there's a whole series of eruptions down the North Rift Zone. So the summit caldera is connected to two fissure zones, and these are where most of the eruptions actually take place. They each extend about 30 miles from the summit, and this eruption here went about 12 miles down the North Rift. In a cross section, so this is actually looking like a vertical slice through the magma chamber, which is the white line. It's very hard to see. In 2011, the dike went to the south. The dike is the blade of lava that projects down out from the magma chamber. It extended to the south, and it came from a zone in the magma chamber that is almost entirely melt, almost no crystals in it. The new dike started in that same area in the summit, and then progressed a time series, progressed to the north, and tapped into the crystal-rich portion of the magma chamber. And the chemistry of the lavas reflects that change in the magma system. The way we actually found the flows is by repeat mapping, and these are a before map, an after map, and a difference map. And these are actually shipboard data, and they detect thick flows. It turns out the thickest flow here is about 125 meters thick. And so the shipboard data is good enough that you can detect changes in the seafloor that are large like that. If you want to do finer and thinner flows, finer mapping and thinner flows, you need autonomous vehicle or robotically collected high-resolution data, and that has now been done after the eruption. We did not have pre-eruption high-resolution data for this zone along the North Rift Zone. We don't want the sound on. Oh well, we're going to get the sound. The flows are really bright black and easy to identify near the edges of thin flows. However, where the flows are thick, they're actually covered with a mat like this that makes it very hard to identify which are the new and which are the old flows. The mat is hydrothermal deposits and bacterial mats. And with time, that will go away. Sorry, we should have checked the sound. There.
Nope.
No?
No, it says mute, but it's still playing.
They won't do it. You're going to have to listen to the music that went with it. There were two eruption styles that we didn't know about before. This is actually an ash deposit, and it's on one of the monuments on the summit. And this was formed from mildly explosive eruptions along the fissure zone. And the last one here shows steam explosions that produced loud sounds that were recorded by the seismometers and other acoustic devices that were out on the seamount. And I'm going to let Scott talk about the volume of the lava erupted can be calculated from those maps that ties to changes in the shape of the volcano that happened during the eruption. And then at the end, will talk about some of the sounds and where they were located that were produced by the eruption. Thank you. Scott, turn it over to you before the sound goes again.
Thanks, Dave. Okay, so the key points for this part of the study were that we were able to forecast the 2015 eruption based on patterns of surface deformation. So by surface deformation, I mean the patterns of ups and downs of the surface of the volcano. As the volcano is recharged with magma, the surface of the volcano swells like a balloon, and then during an eruption, the magma is taken out of the underlying magma chamber, and the surface of the volcano drops. So we can look at these patterns of deformation, and we've been monitoring this and studying the volcano since the 90s. And so we've observed several eruptions at this point. So based on that pattern, we were able to forecast the 2015 eruption successfully. Another point is that after the 2011 eruption, so we've seen eruptions now in 1998, 2011, and 2015. After the 2011 eruption, there was a pretty dramatic increase in the magma supply rate back into the volcano. And that was a bit surprising to see. And that led to a very short interval between 2011 and the 2015 eruption. We also observed a nearly vertical magma conduit. So, and this is where this nearly vertical magma conduit within the larger magma chamber accommodated the inflation leading up to the eruption, and is where the magma was taken out of during the eruption. And then finally, with instruments, these tiltmeter instruments on the Cable Observatory, and these are instruments that measure the slight changes in the tilt or the slope of the surface of the volcano. These allowed us to observe a short episode of southward dike propagation which then stopped, and then the main part of the dike went along the North Rift Zone to the north. So that was an interesting and surprising thing as well. So this record, this plot that I'm showing you here, is a record since 1998 showing the central part of the caldera and how it has inflated and deflated, so how the elevation has increased and decreased over time. So the dramatic drops that you can see in this record are eruptions. So here's the 1998 eruption, followed by a pretty long period of relatively, for this volcano anyway, relatively slow, steady uplift. And then another eruption in 2011, which you can see this drop. So this is a drop of about 2.5 meters. The 1998 eruption was a drop of about 3.4 meters, close to 3.5 meters. And then in 2015, the surface of the volcano dropped by about 2.5 meters as well. And so we actually use this inflation, this pattern of inflation, to suggest, or we came up with a model that the eruptions were triggered at a certain threshold. So once the magma chamber got to a certain level of stress by being filled up by magma, then the magma chamber would then no longer be able to contain the magma, and an eruption or a diking event would occur. So that's the model that we used to forecast the 2015 eruption successfully. And you can see in this plot that the period between 2011 and 2015, the rate of inflation was significantly higher. The center of the caldera was uplifting by about 60 centimeters per year compared to 15 centimeters per year previously. Since the 2015 eruption, the inflation rate has not been quite as high as it was between 2011 and 2015, but it's still pretty high. It's currently inflating at about 50 centimeters per year, which means that if the volcano continues at that rate, we expect an eruption sometime in about 3 years or so. But volcanoes can change behavior, so we're going to be able to keep an eye on this with a cabled observatory. The instruments from the OOI cabled observatory will allow us to watch this in real time and to update our forecasts. And so we should have a much better idea as the next eruption approaches when that's going to occur. And that will allow us to do things like organize responses to go and sample the lava flows and look at the water column and the biological communities directly after an eruption, which is a pretty exciting thing to be able to do. We make these measurements of surface deformation using water pressure. So let me show this short video. The places that we make these water pressure measurements are shown by these dots here. And there's a couple of different types of instruments that we have. They all measure water pressure. Some of our instruments stay on the bottom permanently, and others we carry around with an ROV and make measurements on top of these concrete benchmarks. And we really need a combination of these to get the full picture. The OOI cable has some permanent instruments, 3 of them, shown here in the sort of teal color. And the other interesting thing about the surface deformation measurements is that not only can we use them to make forecasts of eruptions, we can also figure out what the magma dynamics of the volcanic system is. So what I'm showing here is the model from this study fitting to the data. And we find that there is a nearly vertical conduit of a region within the larger magma chamber that accommodated the magma flowing into the system between the 2011 and 2015 eruption. And that was also the source of the magma for the 2015 eruption. And so just to put that into context, this is a map very similar to the one that Dave showed a minute ago that shows the underlying larger magma system. And then the vertical conduit that was the source of the magma for the eruption. It's just one part of that larger underlying magma chamber. Oh, I also want to say that, sorry, let me go back. I also want to say that this also allows us to calculate how much magma was removed from the system during the eruption. And we found that there's about 288 million cubic meters of magma that was removed from the central magma chamber during this eruption. And if we compare that to the amount of lava that was erupted onto the surface, we find that about half of the magma that was withdrawn from the magma chamber did not make it to the surface, so it was stored within the dike below the surface. And finally, another very interesting aspect of this study is there are tiltmeters that I mentioned earlier that are connected to the OOI cabled observatory. And we were able to see from one of these tiltmeters in the center of the caldera that the dike initially propagated to the south, and we can tell that from the tilt record here as the dike moves from the north towards the tiltmeter. The surface of the volcano actually tilts in the direction that the dike is moving. And then when the dike goes past the tiltmeter, the surface tilts in the other direction. So that tells us about that southward dike propagation. And then that stops, and the dike continues to the north for the rest of the episode. And so with that, I'm going to turn it over now to William to give the rest of the story.
So one of the really exciting things about the OOI cabled array is it's allowed us to observe the seismicity from the volcano in real time and observe a seafloor eruption in unprecedented detail. And we were able to track the buildup and the eruption itself using the seismic signals from earthquakes, hundreds of thousands of earthquakes that were occurred because there was motion on faults and because the crust was being fractured as the magma moved. And we were also able to detect the explosions that occurred on the sea floor when hot magma erupted and interacted explosively with seawater. A major discovery was we found the caldera was underlain by an outward dipping ring fault that basically wraps around the caldera. And this was active both before and during the eruption. And this is important because calderas are found in volcanoes around the world, and there's a lot of arguments about how the ring faults work. And while we're not the first to observe an outward dipping ring fault seismically, these are by far the most detailed observations because we've recorded so many earthquakes and it's such a shallow system. And the cable network is still out there recording data, and it has a wide variety of sensors, and scientists are scheming to deploy more on it. And so it moves towards the next eruption. We're going to record that in even more detail. Now, before showing you some of my results, I just wanted to give you a sense of what it was like to deploy one of the seismic network. This is a short period seismometer that's sitting on a pallet, and it's being lifted by the manipulator and arm of a remotely operated vehicle onto the sea floor. The seismic sensor is a cylindrical pressure case that's sitting on the triangular plate, which has 3 legs, so it sits stably on the sea floor. To make the seismometers work well, they need to be leveled to within a few degrees. So this is a ball-bearing level that's been placed on the plate, and 2 of the legs are being adjusted so that it's level. And eventually it's leveled to within about 2 degrees, which is sufficient for it to work very well. The next step is to plug it in. And so this is a cable that comes from the cabled observatory. It has a fancy connector on it which allows you to make power and data connections underwater. And then it's plugged in. And then once it's plugged in, the final thing that's done is to place a sandbag on the cable, because if the cable strummed in ocean currents, that would create noise that we don't want. And now when this is sitting on the sea floor, this is now in a very stable environment. It's a uniform temperature. Unlike land volcanoes, you don't have to deal with bad weather. So we can expect this to operate for a long time. The left-hand slide you've already seen, that shows the caldera, and then in blue the outlines of the 2011 eruption, and in green the outline of the 2015 eruption that went north. The right-hand figure sort of summarizes the results from the seismic study. The black squares, those show the locations of the 7 seismometers that we have right on top of the caldera. Up in the north particularly, you can see on the outlines of the lava flows these purple dots. Those are the locations of a subset of the explosions that we were able to locate. So we were able to, and these occurred as within hours of the onset of the eruption, the lava reached the north, and we were able to observe these and locate them because we can look at the echoes come bouncing up and down through the water column. And that told people where to go and look for lava on the sea floor. The brown, red, and blue dots, those show earthquakes recorded before, during, and after the eruption. And most of the earthquakes recorded are on the west wall of the caldera and on the east wall. And we can look at those in cross-section. And what we see is we see nearly all these earthquakes align down 2 outward dipping faults. And this is actually one ring fault that wraps around the whole caldera. And it's not visible on the sea floor because these actually intersect the caldera, the floor of the caldera, and they've been overrun by lava flows. And what happened was before the eruption, as the volcano expanded, the center of the caldera lifted up, and so the faults moved one way, as shown by the blue arrows. Then, when it erupted and magma moved out, the caldera collapses, and so the motion on these faults reversed. The ring fault also provided a path of weakness which allowed the magma initially to rise up to the surface in the caldera, and then it guided the dike around the caldera till it stepped into the rift. Now this slide is just a summary of all the instruments that are currently on the observatory, and I just want to make the point that in addition to the seismic sensors and the bottom pressure and tilt sensors, there are a wide variety of other sensors. There are cameras, there are instruments to measure the temperature, the chemistry, and the biology of the 2 hydrothermal vent fields. And there are plans to install more instruments. We're very interested in making measurements up in the water column. And so when this volcano erupts the next time, we will have an even larger data set than we have now, and we'll be able to observe not only the sort of geophysics of the eruption, but we'll be able to understand how the hydrothermal systems and the life systems they support are impacted by the eruption. And we'll be able to do that in real time. And I just sort of finished by putting up the contact information of everybody who's spoken, as well as Bill Chadwick, who's at sea, and would have spoken had he been not at sea.
Great, thank you very much. We'll now open up for questions from reporters in the room. If you have a question, please raise your hand and state your name and affiliation. Heather.
Hi, Sarah Kaplan from the Washington Post. I have a couple of questions. I guess the first one is, can you talk about how you forecasted this eruption and how that compares to forecasting the eruptions of terrestrial volcanoes? Is this going to help us predict future eruptions that might affect people?
Sure.
And then I can ask the second one after.
Yes. So Axial Seamount is actually a relatively simple volcano, even though in the images you saw that the underlying magma chamber is actually pretty complex. But it really is a relatively simple volcano, and it has what appears to be relatively repeatable behavior. So our model at this point is really just a simple model that the magma chamber will inflate, and once it gets to a certain threshold, it erupts. So that's sort of our idea, or our purpose behind studying this is so that we can understand these simple systems first, and then we can move to more complex volcanoes and apply similar ideas. So we should certainly at some point in the future be able to apply these same ideas to terrestrial volcanoes. And there are people that are working on terrestrial volcanoes currently as well, and there has been some successful forecasting of some volcanoes, especially like in Krafla volcano in Iceland, for example. But the forecasts that have been done on land so far, at least as far as I'm aware, are much shorter time scales. So on the order of forecasting something erupting a few weeks in advance, whereas we were able to forecast at Axial months in advance. So the time scales are quite different. So we should be able to, though, take what we've learned here and continue to refine our models and then move to more complex volcanoes over time.
And also, can you talk about what it looks like when an undersea volcano erupts, like for readers who might just picture like the traditional stuff spewing into the sky? What does that look like?
That's a good question. Actually, underwater volcanoes make a mess. The water column is full of small particles that are emitted during the eruption, little bits of glass, little bits of bacteria from the underground hydrothermal systems, and the water gets to be very cloudy. So there actually was an eruption on the East Pacific Rise that an Alvin dive went to in 1992. They probably dove right in the middle of the eruption. They couldn't see anything, and the sub was brought back to the surface. And then they went back a month later and could actually see what had happened. We have not been at Axial when it has actually erupted. We get there usually 3 months later or so on the 2011 and 2015 eruption, actually all 3 eruptions, several months after the eruption. And the water is still very turbid, and so the video is not terribly good that one can get, and it's hard to observe. And as I pointed out in the pictures, the bacterial mat that forms on the lava flows makes it very hard to figure out what's new and what's not. It's actually easier to tell a few years later when all of the bacterial activity has calmed down a little bit.
Can I ask one more question? Sorry. When you had that chart showing the various rates of inflation before each eruption, how were you able to tell how the caldera was inflated before, like in 1998? Were you not, the presumably the array wasn't cabled up at that point. So like, how did you know that it was inflating?
So yeah, the cabled array really only came online just before the 2015 eruption. Prior to that, we have been putting battery-powered instruments down, and every few years we'll go out and pick them back up and change the batteries and put them back down. And we also go out with ROVs and drive around every couple of years with instruments that we measure water pressure on top of these concrete tables that we put down on the bottom. And we've been doing that since 1998. So that's how we did it before. The Cable Observatory will allow us to observe what's going on in real time, but there's still not quite enough instruments on the Cabled Observatory to really be able to track what the magma is doing underneath. So we're actually going to have to continue to do these battery-powered and ROV surveys as well to really get the full picture.
Harvey?
Harvey Lyford, freelance. For Professor Nooner, when did you make the prediction of the 2015 eruption, and how precisely did you make it? Did you say April 24th, or did you say sometime in 2015, or what?
So we made our forecast initially in September of 2014 on a blog. We have a science blog that we're keeping up to date. And we said sometime in 2015. So that was our accuracy.
Thank you. And I have a question for Dr. Clegg also. Can you say something about the hydrothermal chimneys that Mbari discovered, and what you know about the life in them?
The ones at Axial?
At Axial, yes.
We have actually, most of the chimneys were known from dives done many years ago. Once we had generated some 1 meter resolution maps, we discovered that one of the fields that people had been going to for many years actually was more extensive and had a whole lot of additional chimneys that they had not ever gone to. And so that's one on the south side. It has been networked with instruments, but the hottest vent on the volcano that we know of is one of these that was close by but had not been seen before. So and that was found in 2011, I think, 2009 maybe. Okay.
So I've got a detailed question, I suppose. What would be a comparable terrestrial volcano, and why is it more difficult to instrument terrestrial volcanoes than this one, or land-based?
Well, I think comparable volcanoes would be volcanoes in Iceland or volcanoes in Hawaii. And I think one of the challenges of instrumenting land volcanoes, and they're often in very remote areas, and so you have to keep instruments running. You often have instruments in hostile weather, so they have to run through that. Whereas on the seafloor, it's hard to deploy the cabled observatory, but once it's there, it's a pretty stable environment, and so the instruments keep working. And and many volcanoes are dangerous. So somewhere like Mount St. Helens, it's very dangerous to have people go into the caldera of that volcano to even deploy instruments. So there's a limited number of instruments. Whereas here, we have the instruments right on top of the action. It's a very tight network. So it really gives us pretty unique observations.
We have some questions on the chat.
We have a question from Casey Deemer at Live Science. Casey asks, while Axial is far from posing a risk to humans, has anyone looked into how the surrounding ecosystem is impacted by these eruptions?
That's you, I think. I think that's me. I think that's me. There are biologists who are looking at the impacts. Many of the instruments that are on the Cabled Observatory were deployed specifically to look at changes that eruptions or even earthquake swarms would trigger in the hydrothermal vent communities in particular. And so far, those instruments were mainly not really online when this last eruption happened. So that's probably going to be something we're going to get the next eruption. We'll really be able to see whether there were changes in the fluid flow that then affected the animal communities and particularly the microbial communities.
And I would just add one thing. When you have these eruptions, there are things called mega plumes that form, where you have large amounts of hot water rises up into the water column. There are arguments about how mechanisms by which those form, but they contain a lot of microbes which apparently appear to be flushed out of the subsurface. So it's very important that we get there quickly enough to observe that process happening, because these have never been observed actually forming. And they would basically provide a window into the subsurface biosphere. And so I think one thing that's going to be very important for this observatory is to try and add moorings and potentially an autonomous underwater vehicle that can basically respond very rapidly once we detect something with the seismic or pressure network.
One more question.
We have another question from Dagmar Rohrlich from Deutschlandfunk. Dagmar asks, could you please explain a bit more about the new eruption types, specifically what makes them new?
Yeah, that was definitely me again. We had these steam explosions that are recorded as sort of an acoustic signal through the water column that William showed on his slide. Those are something that we hadn't really seen before. We have encountered these little craters or areas of broken up rock previously, but they're very rare. And this eruption has literally tens of thousands of them. We don't really understand yet why there are so many with this eruption, because they seem to be just steam, in which case all the eruptions are happening into water and they all are hot lava, and that interaction seems to me it should have produced steam eruptions or steam explosions. But we have not seen these but a handful of times in many, many ROV dives on the volcano. So this eruption was unique in that way. So that was one of the types of eruptions that we had not really documented thoroughly yet. We suspected that they occurred. The second type, again, we have been working on, a number of us have been working on sort of pyroclastic eruptions where there are big bubble bursts of magmatic gas that are coming out at the vent that produce small amounts of ash, basically, fine glass particles. And we had never been able to tie those to a single eruption, and here we got the opportunity to find that ash on top of the monuments that had been deployed after the 2011 eruption. So we know they're tied to this eruption, and we can actually then figure out what part of the fissure system produced that ash and how far it was transported in the water column. It turns out it's about 2.5 to 3 kilometers that these ash particles were transported through the water. So those are the aspects that we had not really had details of before.
Hi, I'm Katrin Weiss from City College and Earth Rocks, and my question is about seismometers that were placed down, and you showed the video of how they were placed, but they seem to be mechanically set, and they are on a crater that is in fact tilting, and so I'm just curious, when you go back and look at them, what kind of displacement are you finding on those, and is it significant?
I'm not aware, I don't think they'll be displaced very much. So the tilt instruments are very sensitive instruments which measure tilts of a fraction of a degree. The seismic instruments need to be leveled within, I think, about 5 degrees to work. So it would have to be pretty catastrophic tilting, maybe very close to a fissure or something, for them to be effective.
Rick Lovett again, freelance. You mentioned twice the bacteria appearing on the lava and then disappearing. This runs counter to what one would expect in a terrestrial environment. What's going on?
Okay, the new flows, particularly if they're fairly thick, they actually are cooling over a period of many years. And the cooling takes place by water convecting through the flows, particularly in between all the pillows. And that warm water supports a bacterial community. And so as the flows cool, the bacterial activity on the flows diminishes. And most of it seems to be right at the beginning, so their cooling is very rapid and then a very long tail as it continues to cool. So we've been to flows 7 years or 8 years after the eruptions, and they're still cooling. There still is some bacteria, but instead of covering everything, it's just in little cracks here and there. and it makes it a lot, then the lavas look black and shiny, actually. The bacterial mats actually either are consumed by megafauna or just they blow away. They're very fluffy, so the smallest current would carry them away, I think, too. So they do disappear with time.
Are there any other questions from reporters in the room? Are there any other questions on the chat? Okay, thank you very much. That concludes our press conference. Up next, Dawn Science Update at 10:30. Thank you.